Okay, in this video, this will be our first video on integration by substitution. And in this section, we are going to learn a way in which we can find antiderivatives of functions in which you got to them by taking the derivative using the chain rule. Okay, so the basic idea behind these types of problems is recognizing patterns for derivatives. Okay, so if you're looking at your notes handout, we have an integral of little f of g times g prime. Okay, so when you look at that, you should be able to recognize that somehow you took a derivative of a composite function and you used the chain rule to get that derivative. Okay, so we took the derivative of the outside function. So if big F was our outside function, we took the derivative of that and we got this f of g and then times g prime. So we would want to recognize this whole thing as just using the chain rule. And whenever you see that pattern, we will use this method to be able to undo or do the inverse of that operation. So we want to take an antiderivative. Okay, so again, and then this one, whenever we take that antiderivative, we end up back at big F, where big F is the antiderivative of little g. Okay, and again, you can always check your answer on all these, where if I now take the derivative of this answer, if I take that derivative, the derivative of big F was little f of g, and then times the derivative of the inside. Okay, so looking at the first example, we have the integral of 2x times the quantity x squared plus 1 raised to the fourth power. Okay, so when you're looking at a problem, you want to always recognize the pattern. So what was the original outside function, what was the inside function, and where is the derivative of the inside function? Okay, so when we're looking at this problem, if we focus in on this right here, we see that we have some function raised to the fourth power. Okay, so I'm going to label that as a u. Okay, so the x squared plus 1 is like a function u in terms of x. Okay, now we also need to know what is the derivative of the inside function. Okay, so if we look at x squared plus 1, the derivative of that inside function is 2x. Okay, so this right here represents the derivative of u with respect to x. Okay, so du dx. Okay, so now using that, we want to sort of fit this pattern and work backwards. Okay, so if I have, okay, so off to the side here, I'm going to write down that u was equal to x squared plus 1, and du is going to be equal to 2x times dx. Okay, and if you're not sure where that came from, we had that up here, we had that du dx was equal to 2x. So if du dx is equal to 2x, du is equal to 2x times dx. All right, so now looking at our problem, if we substitute in these u's and these du's, and we rewrite the problem, we have the integral of, well, the 2x and the dx, this and this, were the same thing as our du. Okay, our x squared plus 1 to the fourth, that piece, this piece inside x squared plus 1 was the same thing as our u. So rewriting then our integral, we're going to write this as u raised to the fourth power, and then that is going to be times du. Okay, where u was equal to x squared plus 1, du is equal to 2x dx. Okay, so I have not changed my problem at all. All I have done is rewritten it in terms of new variables u and du. Okay, so now once you have this written in terms of u's and du's, you should be able to look at your new problem and say, can I use my integration rules to integrate this? So here we just have u to the fourth du. We do know how to take an antiderivative of that one, right? Just use the power rule. So that will give us u to the fifth divided by 5 plus c. Okay, so our answer in terms of u is u to the fifth over 5 plus c. We want our answer to be expressed back in terms of x. So now plugging back in for our u function, u is equal to x squared plus 1. So this will be x squared plus 1. That's all raised to the fifth, divided by 5, and then plus c. And of course, you can always go and check your answer by taking a derivative. Okay, now after a while, once you've done a whole bunch of these, you'll start to recognize these patterns, and a lot of this you're going to be able to do sort of in your head. I would suggest you still write out all of these steps so you understand what's going on. Okay, so now example 2, we have the integral of 3x squared times the square root of x cubed plus 1. Okay, so again, the first thing you want to do is identify what was that inside function. Okay, well, we see outside function of the original problem had something to do with a square root. The inside of that was x cubed plus 1. So again, the inside is going to be what is your u. Okay, so u is going to be equal to x cubed plus 1. Okay, then we want to look and see what's left over in our problem. We have this 3x squared and we have a dx. Well, if we take the derivative of our u function, so if we find du, we take the derivative of our u function, we get 3x squared times dx, okay, which happens to be what we still had left over in our problem. Okay, so now we rewrite or substitute in. We have an integral. Okay, so now in place of the 3x squared dx, that's going to be our du. Left over, we still have a square root of, inside the square root, we have u, and then times du. Okay, we know how to take an antiderivative for the square root of u because that is going to be the same thing as the integral of u to the 1/2 du. So this will give us u to the 3/2 divided by 3/2 plus c. And this is the same thing as 2/3 u to the 3/2 plus c. So there is our answer in terms of u. If there's any sort of simplifying, you always want to do it in terms of u because it'll be easier when you have u's in there rather than another function. And then the very last step, then we go ahead and plug back in for u. So this will equal 2/3. In place of u, we plug that back in, which was x cubed plus 1. That's to the 3/2, and then plus c. All right, example 3, we have secant squared times tangent of x plus 3. Okay, so something like this, the first thing you want to do is see if one of the parts is the derivative of the other part before you start trying to replace secants and tangents with something else. Look at the integrand, is one part the derivative of the other part? Okay, so hopefully you recognize that secant squared is the derivative of tangent. Okay, so as long as you recognize that, we know that everything here in parentheses is going to be our u. So we'll label u is equal to tangent of x plus 3. And then when we take the derivative of u, we get secant squared. And then the derivative of 3 is just 0, so secant squared of x dx. And if we look back up at our integrand, secant squared x dx was exactly what was left over in the problem. So we have our u and we have our du. All right, so now we'll go ahead and substitute in or rewrite. So now our new integral, we have our u function in purple, so that was just tangent of x plus 3, that was u. And then everything in pink, everything else was our du. So doing u substitution here, that made everything a lot simpler. All we have now is an integral of u du. Okay, so now we can go ahead and take an antiderivative of that. Oops. U du. Okay, so taking the antiderivative of u du, we get u squared divided by 2 plus c. And now we can go ahead and substitute in for our u. Our u was tangent of x plus 3. That's going to all be squared over 2 plus c. Okay, example 4, we have 3x squared times sine of x cubed. Okay, so again, you want to look at the problem and think to yourself, okay, what is our u and what is our du? Okay, so hopefully you will be able to answer that. The x cubed should be our u. And then when we take the derivative of our u, du is 3x squared dx. Okay, so now when we look at our original problem, we have sine of u, and then this 3x squared dx is our du. Okay, so now we're going to rewrite our problem in terms of u. So we have sine of u times du. Now we go ahead and integrate. So the antiderivative for sine is the opposite of cosine, and plus c, and then we can go ahead and substitute back in for our u. So we'll get minus cosine of u, which was x cubed, plus c. Okay, so next one, and this will be the last one for this video. Last one, we have the integral of sine of 7 theta plus 5 d theta. Okay, so this one's just a little bit different. When you look at the problem, again, what is the part that you want to be your u? It should be an inside function. Okay, so our inside function here is going to be the 7 theta plus 5. So u equals 7 theta plus 5. Our derivative for u is just 7 d theta. Okay, so this one's a little bit different because we have the d theta, but we do not have the times 7. Okay, well, 7 is just a constant, so that's okay because we can always multiply and divide by a constant. Okay, if I want my du to be 7 d theta, that's fine. I can multiply my integrand by 7. It's just a number, so I can also come out to the outside and divide by 7. Okay, so we're just multiplying by 7 and dividing by 7. We have not changed the problem at all. We're just balancing things out so that we can get our du to be equal to 7 d theta. Okay, so now we go ahead and rewrite in terms of our u. So out in front we have this 1 over 7 times the integral. We have sine of u, and then we have the 7 d theta, that is our du. Okay, so then we go ahead and take the antiderivative. So the antiderivative, we have antiderivative for sine is going to be minus cosine, so we'll have a minus 1/7 cosine of u plus c. And then we can go ahead and plug back in for our u. We have negative 1/7 cosine. Our u function was 7 theta plus 5 and plus c. Okay, so let's see. I think that's all I wanted to do. Oh, Okay, so for this video, that'll be where we'll kind of stop. Next video then, we're going to be discussing how to do a complete change of variables. One, if you have a definite integral, and then we've got some other problems where you've got to do some extra algebraic manipulations to be able to get the integrand into the form that you want it to be in. Okay, so that'll be in the next video.